if you understand the notes from the last lecture, you'll have a lot easier time understanding what's going on now, and it'll be much easier preparing for exams. But if there's something you didn't understand, you can clear it up at the beginning of the lecture. So it's a perfect time to clear up anything that you might not have understood from the last lecture. And believe me, it's normal not to understand everything and just ask questions. So there's no shame in asking questions. Okay, so with that, are there any questions? Yeah?
The last lecture, we drew a reactor and we had coming out of it flue gas.
Yes.
What's that?
Flue gas is basically what comes out of the chimney and gets put out to the atmosphere.
So is it?
It's basically the stuff that comes out. It's not a processed fluid that we're going to collect. It's a fluid that we're going to dispose of. And typically you use it for gases as opposed to liquids. So some gas stream, that's essentially the junk.
Is it the same, you know, with the refineries, they burn stuff very top?
Yeah, that's their flue gas. It's not the stuff that's being burned, it's what comes out after the burn.
So it's more of a general term, as opposed to, it's more of a general term?
It's a general term, yes, it's a general term. It has nothing to do with the seasonal flu. Are there other questions? Okay, one other comment I'm going to make is, we're going to be doing some mathematics in this class, because it's a mathematical class, and there's this unfortunate thing that the people who do kinetics and the people who do control use different symbols for the same thing. Now, that's not my fault. But what I'm going to try to do is be consistent with the way kinetics people do it, so as not to confuse you with your other class. But you can use whichever one you want. Your textbook uses the ones that the control people use. So you'll have both versions. You'll have the version with the kinetics version and the version with the control version. Okay, so we were talking about control. Again, feel free to interrupt me. By the way, if we want more light there, maybe someone can open the shades back there. I know over here it interferes with the blackboard, but maybe over there, excuse me, it just brightens up the room a little bit. Sorry, I just happen to like light. Are they broken? Okay, let there be light. Somebody, to quote someone famous, let there be light. I'll wait until somebody light. Okay, so there are various types of control strategies. And as we said, one goal in control is to identify the variables that you want to be in a certain range, and for each one of those, to identify at least one way of adjusting something else that will influence it. Well, that's not necessarily the whole story, that's just a basic. So let's imagine that I have three distillation columns in series. So I need to do a complicated separation. And in this separation, I can control, let's see, yeah, there's a heater that goes in. So this is a heater to heat up the feed. And I have a valve here that controls the heat. So here I have an input stream that goes into a distillation column. The bottoms go into another distillation column, get separated. The bottoms go into another distillation column, get separated. And of course, I'm interested in the product here. I'm interested in that. Now, let's imagine that the product isn't coming out what I want it to be. So what I could do is, let's say, for example, there's a problem, and I know that if I heated up the feed more, then I would get a better product stream. So what I could do is do control this way. That is, I could make my measurements here, and then I could control the input over here. Now, what would the result of that be? The result of that could be, if this is my set point, so here is time, and here is the output concentration, let's call it C3. C3. And this is the set point, the goal. I imagine if I'm doing my sensing down here and controlling up here, that by the time I notice that the concentration is way off, and then I try to correct it, it's going to take a while for that information to get back in here. So what can happen is I can really go way off before I start getting back down. I can have a long excursion. Another possibility might be I can measure the control here. And let me use a different color for that, just because I have many colors of chalk. I can also measure the concentration here. And chances are, if there's some problem with the feed here, I would notice it here already. I don't have to wait till I get here. Yep.
What is AC?
AC? I don't really know what A is, but C is control, is concentration. C stands, so when I want to measure temperature, I'll write AT, and that's just the A is sort of the convention. I don't know what the A stands for. But the main thing is what comes after the A. So for concentration, it's an AC. For temperature, it's AT. For pressure, it's AP, etc.
That's just where you're measuring that quantity.
Right, it's one of the sensors. If you remember, you need sensors, and this is one of the sensors. So usually in these diagrams, I represent a sensor by a circle with a line. So my second control strategy might be to measure the concentration and to compare it with what I would like it to be, not over here, but what I would like, say, C1 to be. And if it's off, then I can immediately adjust this. Sorry. So if that's the case, then presumably, whatever problems I have down here come from the fact that the feed was at the wrong temperature. So if I can correct that once I see an error here, chances are that my excursions here will be much smaller. So there's a choice here. In both places, I have a valve that I can adjust. In both cases, I am doing a measurement and correcting based on that measurement. But you see there's a strategy. Whether should I only rely on the measurement here, or should I rely on this measurement as well? And actually, a clever way of doing it would be to rely on both measurements. We rely on this one, which should speed up the response. But we don't want to give up on this measurement. This measurement is, of course, the final, the absolute test. So if we do both, chances are we can have much smaller variations. So that's already a notion where strategy makes difference. Let's look at another situation. Let's look at a reactor where, so I have, let's just see, I think I want a level control. Is that correct? Yeah, I want a level control and a heater. So I have fluid coming in. I've got a heater, a level control, which I measure. AL for level control. And I control the pump. And then I also have a heater. And I have a temperature sensor, AT. And if I don't like that, I can control here. So here I have a situation where I have a reaction in the reactor. Let's say it's exothermic. If it's exothermic, then it starts to heat up. And here I might have cooling fluid to cool it down. So if the temperature is too hot, I might increase the flow of the cooling fluid. If it's too cold, I may decrease the flow of the cooling fluid. Moreover, I want to control the level. So if the level gets too high, then I open this valve and I pump more fluid out faster. If the level gets too low, I crimp down on this. What could possibly go wrong here? And of course, I'm going to assume I have a mixer so that everything is uniform. I have good mixing. So what issues could come up here? So this was a question of strategy. And this is a question of issues. And this is going to be analogous to the situation I spoke about last time in the shower, where you're adjusting the temperature in the shower. Let's say this reaction is too slow. So I put the sensors in the right places. But my algorithm for how quickly things should react is sluggish. If it's too slow, then by the time this valve opens up, the tank will rise above where it should and may overflow. If when it's low and I need to shut this valve, and I need to shut the valve so that fluid doesn't flow out too quickly, the tank might get so low that I quench the reaction. So obviously too slow is no good. On the other hand, what happens if it's too fast? If immediately as this goes to the top, the valve goes wide open and I pump the whole thing out. So the level might start out going a little bit above here, and if I overreact, the next time it's going to come way down here. Now, when it senses that it's too low, because remember, there's a time lag. There's a time lag between a slight time lag between the sensor and the time that the valve can open and close. Typically, valves open and close in fractions of a second. But if the pumping speed is high, that could be a long time. And you could imagine that the amplitude of the error from the design level would grow with time, not shrink with time, if I'm too aggressive. So I have to be careful about not being too slow and not too fast, and that depends, of course, on the situation. How about, any questions on that? Okay, let's say I have 3 CSDR, another situation. I have 3 CSDRs in series. Three CSDRs in series. And what else do I have in the picture? I have, yes, so I can heat up so I have a feed here, but I can also spike the feed. So what's the idea here? I have a feed with a low concentration of A, CA. And here I have a line with a high concentration of CA, where A is my reactant. And I'm going to measure the concentration here. So one type of control, so let's look at different control strategies. Strategy 1. Strategy 1. Feedback from C3. So here's C3. And I do feedback control from here to here. So what does that mean? That says if C3, if the concentration of my product, say CB, let's call it CB3, where B is my product. If I don't have enough product, B, then what I might do is open this valve a little bit to spike the feed to get a little more A in here. More reactant means a higher concentration of reactant. means a higher reaction rate. Well, what happens with strategy 1? With strategy 1, if this is CB3 versus time, and here's my set point, my goal, what happens is I could have a downward excursion, which I then try to correct, but I might never succeed if I don't have a good algorithm in completely correcting it. And this is called an offset. And we'll talk in great detail about that a little bit later on in the semester when we get to control. What you'll notice in the next few weeks is we won't get to control for a while. Before we get to control, we have to model. So we're going to learn how to model systems, and then we'll learn how to put control into the models. But I want you to keep in the back of your mind that when we get to control, we're going to encounter offset. Now, if we have a more clever algorithm, strategy 2, so it's not just feedback, but plus what I'm going to call integral control. Again, I'm going to define that much later in the semester. I just want you to know that something like this exists. Then, we'll call strategy 2 the pink one. So it's the same control, but I have strategy 2. Then, when I have integral control, then it might go something more like this. And if I add integral to feedback control, I can get back to my set point. Again, you don't know what integral control is yet, and you don't know why we need it. This is, as you know, like when you watch those continuing series on TV, coming attractions. This happens later in the season. Finally, there's strategy 3. Make that one green. And strategy 3 says, well, maybe we can measure the concentration here. That is, measure the concentration before it goes in the reactor. Or actually, probably a better place is to do it here. Let's measure the concentration here. And if that concentration isn't good enough, then immediately change the spiking. And actually, the one in your textbook, and let me stick to that, is you measure the concentration here. So if the stream coming from another part of the plant has a lower concentration than we expect, we don't have to wait to see a problem down here. We can try to correct it immediately. And this is to add feed forward. FF is feed forward as opposed to feedback. And if you have the feed forward together with the feedback, then chances are you never get this long excursion. The minute you get a little excursion, you correct it. So notice here the issue is where you put your sensors in. Here the issue is how you tune your sensors. And here the issue is what type of control do you use? Is it feedback or feed forward? So 3 issues here. Where do you put your sensors for feedback? How do you tune your sensors for feedback? Is feedback enough? And these are just potential issues. All these things we will get to in great detail when we're prepared. Are there any questions on that so far? Yep.
Why would feedback not be enough? Why would we get an offset and never control?
Feedback will generally alone will not be enough. Simple feedback will not be enough because you can frequently get an offset. Feedback alone, if it's too aggressive, can give you overshoot. Feedback alone, if it's not aggressive enough, will be too sluggish. So feedback is a key thing, but it has to be, sometimes it's not enough to get to your goal. Other questions? And we'll see that in great detail once we have models that we can see it in terms of those models. Okay, so now from this little discussion, we can refine our goals and make them a little bit more technical. We had these sort of general goals last time. Once we've taken care of safety, environment, and equipment protection, when we talk about the process, we can say a technical goal we have is, yes, we want to get the product to spec, but we want to do it with minimum variation. We don't want long excursions. And we don't want it to take forever to get back to the set point. So a more refined goal is we would like to minimize the variation in the controlled variables. Minimize that variation. We would like, for a maximum profit. In order to do that, we have to understand a little bit about the system, the dynamics of the system. We have to understand how the system works. And even here from these pictures, you see that we're getting some, by looking at them, we're getting a little bit of a more deeper understanding than just saying, oh, feedback. We're seeing what issues come as subtexts under feedback control. And of course, the control engineer has to design a system that's controllable. Here you can see, do we put the extra sensor here or just sensor here? That's a design issue. How do we design the control algorithm? Do we also use feed forward? So there's hardware and software. The algorithm of how to respond is software. And that's usually based on an understanding of the system, on a model of the system. So that brings us to, if we need an understanding of the system, we need models. And we should talk about what is a model and what kind of questions do we ask about a model. Well, the first question is, as we said last time, is what are the control variables? What variables do we want to influence? Which variables do we want to control? Which variables can we manipulate? To control them. Yeah. Okay, I'll try to write bigger. Thank you for reminding me. I'll write bigger. Can you read what I've written so far? Or do you want me to read it to you? Sure. Which variables do we want to control? And which variables can we manipulate to control them? Naturally, these are called the control variables because they're the ones we want to control. And these are called the manipulated variables because these are the ones we want to manipulate. For every control variable, we need at least one manipulated variable. We also have to ask, over what range can they vary? Can these variables vary? Safely vary. And that brings us to the operating window. And we know operating window often has to do with safety or equipment damage. We can't just allow them to vary as much as they feel like. We want to control that. And then, as we see from these discussions, how good is feedback at doing the job? Or do we have to do something, or do we have to modify the feedback, make it a little bit more intricate? Now, of course, we need, once we've answered those questions, we need to have an algorithm, a response algorithm. And with magnitudes. A response algorithm says, what I've measured is not what I want. What I've measured is not what I want. I need to adjust the valve. How much? How much do I do it? That's an algorithm, which you, the control engineer, design. And we saw the consequences if you overreact or underreact. And that gives you something about the speed of the response, and it could give you the shape of the response curve. So what we find is the speed of the response and shape of response curve. So here you see a response curve. These are things that you might want to calculate. Yes? Can you just tell me your first name when you ask a question?
Frankie.
Frankie?
What does number 4 say?
Number 4, response algorithm, left the E out, with magnitudes. So you have to design the algorithm. If the sensor isn't giving you what you want, it has to react by doing something with valves. How does it know what to react, how strongly to react? Does it shut the valve all the way, 10%, 5%? You have to design that algorithm. Okay, so these are our goals. Is there one other? Yeah, and also, again, this is having to do with the range. When it comes to this range, remember, we're talking, the range could be safety, and it could also be equipment damage. So for example, if it gets really hot, you might damage your sensors, destroy your sensors, or you might affect the material that makes your reactor. You might also, something that's quite sensitive is if you have a catalytic reaction, you might damage the catalyst. So your equipment may be fine, but there's no reaction anymore because you killed your catalyst. So those are things you want to keep in mind, and that tells you the operating window in which you can work. So now if we need a model, there are lots of types of models. Let me number the boards so that when we take pictures, you know where to order them. So models. So there could be, there are mathematical models and experimental models. That is, you can try to mathematically describe your system, or you can just do a bunch of experiments at many different concentrations, many different temperatures, and just make graphs. Sometimes if your system is too complicated to model mathematically, you may have to rely on an experimental model. Sometimes if you do a mathematical model, it could be fundamental or empirical. Fundamental means it's based on first principles. Empirical could mean, well, gee, first principle is too complicated. I just have some correlation, which in your transport class, you did fundamental models, but sometimes you had correlations. You had correlations for certain of the dimensionless quantities. Should it be a steady state model or a dynamic model? Well, in this class, it better be a dynamic model. Because we're looking at things changing. Steady state models, well, we're not generally going to be at steady state, although many times you could be at a quasi-steady state model. So, there's something called the Boussinesq approximation, which you may have heard about in the transport class, that is, assumes somewhat of a quasi-steady state in an unsteady problem. But we'll go through examples of this in the class. Then we also have lump parameter versus distributed parameter. So for example, a lump parameter might be a CSTR, where you assume that the system is well mixed, that there's no spatial variation. On the other hand, a distributed parameter might be, well, it's really not perfectly mixed. Well, what does perfectly mixed mean? Can you ever perfectly mix anything? Not really. You're going to mix it, and you hope that it's going to be well mixed. What is well mixed? So what does that actually mean, well mixed? Well, as in all science, when you say well mixed, it's relative to something else. There's no absolutes, it's relative. So there's a certain time scale that you need if you have a mixer to mix stuff from one part to another. What do you compare that to know if it's well mixed? Well, if you have reactions going on in your reactor, in your CSTR, the reactions have a rate constant, which I think you've had in kinetics, even in physical chemistry, in probably organic chemistry, you had some basic kinetics. And you're going to have it in kinetics now in your reaction during class. There's a rate constant, and the rate constant has units of inverse time. Plus, maybe other units in it, but there's a time scale in your rate constant. So each reaction has a time scale, because it's in the units. And when we say well mixed, what we mean is that the time scale for mixing stuff at the bottom to the top and the sides, that time scale, which is a fluid mechanics time scale, derived time scale, is much faster than all the time scales of your reaction. So if I'm a reaction, I think the place is well mixed. But if I were another reaction that was a lot faster, I would say, no, here there's a high concentration, there's a low concentration. But if I'm sluggish and I don't move that quickly, if I'm a reaction, by the time I notice what's up here, it's already mixed with what's down there. So is that clear? That's what well mixed is. If I cannot assume well mixed, then I need a distributed parameter. And typically in a CSTR, when you're looking at steady state equations, these equations are algebraic. The CSTR equation is an algebraic equation, there are no derivatives. But if I look at a distributed parameter system, like in transport 2, then in the mass transfer part of transport 2, I've got derivatives. I've got d squared c dx squared. I have a diffusion term, the second derivative. And I may have a flow term, the velocity times the derivative of concentration with respect to position, u dot del c. So distributed parameters introduce more derivatives. This can be algebraic. Obviously, if I have a time-dependent problem, then I have a ddt here, so this becomes an ordinary differential equation, but these are partial differential equations. So distributed parameter systems are obviously more challenging. And of course, then there is the issue of, do I solve them analytically or numerically? Or analog? The third one is probably the one you're least familiar with. In analytic solution, I think we all know what that is. That's where we get a solution that we can solve on a piece of paper. If it's too hard, then we can try to solve it on the computer. We plug in numbers for everything and we solve them on the computer. Analog is not something that's done too much these days, but we'll be using a program later on in the semester called Simulink, which is part of MATLAB, where it's essentially the same idea as an analog computer. All the computers we use today are digital, but once upon a time, like 50 years ago, when the digital computers were really slow, they had what's called analog computers. And they would have a box that would have for example, a box that they would call an integrator. They would have a voltage coming in, and what the box did with circuitry was it would effectively add up the voltage as a function of time that came in. So if I had voltage coming in, what came out was the integral of that voltage. They would also have other with circuitry that would take derivatives. So what you would do is you would write out your equation, and wherever you saw a derivative, you would take this derivative box and stick it on the shelf. And wherever you saw an integral, you would take an integral box and stick it on the shelf, and you'd connect them with wires. And then you would just look at the voltage that came out, and that would be the solution to your equations. So that was called an analog computer. No one does that today, but in Simulink, you have these boxes on the screen that you can hook up in the same way that people in the old days used to hook up with wires. And that's kind of fun to do. But the question is, do we do analytic or numerical? Well, let me give you a hint on that before we go into great detail. Why would you solve a problem analytically versus numerically? Anyone have a suggestion?
So you can apply
First name.
Yard.
Yard?
If you solve it
if you solve the problem analytically, you immediately see the dependence on the variables. So you know if a variable appears in an exponent, well, the solution is going to be really sensitive to that variable. If it appears just multiplying the whole thing, then you know it just scales the problem. Immediately from an analytic solution, you see how the answer depends on the variables. If you solve the problem numerically, you lose that intuition. You just have to solve it for lots of different numbers. But sometimes it's just too hard to solve analytically, so you're stuck doing it numerically. So those are some of the advantages and disadvantages of doing that. Okay, so let's talk for a minute about fundamental models versus empirical models. Why would we like fundamental models as opposed to empirical models? Anyone have a suggestion why they like fundamental models?
You could generalize.
Name.
Oh, Renee.
Renee.
Yes, you could generalize them, be more applicable to different systems.
What exactly do you mean by that?
I mean, like Navier-Stokes equation, right? It's more an analytical way of looking at things from first principles.
Okay, but what do you mean by apply to others problems? That's the one what I want you to explain. Rather than give me an example, explain to me what you mean by that.
So for example, if you look at one thing, right, and you look at the fundamental variables that control that system, gravity, viscosity, density of the liquid, flow rates, you can apply it to different other types of tanks based on.
Okay, so I think what you're saying is you can extrapolate. So if I have measurements in this range between here and here, and I have a fundamental model that I think models the physics of what's going on, then I can more comfortably guess with my model what's going to happen here and what's going to happen here. So I think that's what you're saying, is that you can have some confidence in an extrapolation. If I have an empirical model that doesn't have any of the fundamental physics in it, I'd be very careful about extrapolating, because I don't know if the same thing's going on here. That is, in my empirical model, I may have neglected something because I don't know what's really going on. That's not important here, but as soon as I go here, it may be the dominant effect. So I like fundamental models because it's based on an understanding of what's really going on. And therefore, I have more confidence when I do an extrapolation. Well, what types of equations are there in fundamental models? In physics, there are three types of equations. Your physics teacher may have told you this. There are laws of physics. There are conservation laws. And then there are constitutive equations. Can anyone tell me a law of physics?
Gravity.
Gravity's a word, not a law.
But anyway,
When it's object in motion stays in motion.
I'm sorry?
An object in motion stays in motion.
An object in motion in constant motion stays in the absence of forces stays in motion. Whose name is associated with that? Newton, Isaac Newton. Newton's laws of motion are laws of physics. Notice Newton's laws of motion have no parameters. They always hold, whatever always means, and they have no parameters. Newton's second law, F is equal, the force is the time rate of change of the momentum. There's no parameters there. In any given problem, I need problem-specific constitutive equations to tell me what the forces are. They have parameters, but F is equal to ma has no parameters. A body in motion, in the absence of external forces, remains in motion. No parameters. In kinetics, we don't really have a law of physics, but what we do have is something similar in kinetics, is we have species balances. So a species balance, if I have a reaction, species A is not conserved, but I do have an equation, say the CSTR equation. which I will derive for you, probably next time. The CSTR equation has no parameters. It says the space, have you had that, the CSTR equation already? Okay, well, I will derive it for you. If you have a CSTR or a plug flow reactor, then you have an equation that says the space-time, whatever that is equal to some function of the rates. It's some integral of the rates. But I don't tell you what the rates are. The rates are something that in every reaction that you run in the reactor are going to be different. But the general equation, which is a species balance, it's telling you roughly, it's relating the concentration of your species coming in and your concentration of species coming out to the parts of the reactor, the type of reactor. Those are species balances instead of laws of physics. What about a conservation equation? What's the conservation equation? First name? Ismail? Yeah. Conservation of momentum. In the absence of forces, there's no momentum, change in momentum, but that's a special case of the law of physics. So momentum is not always conserved. If there are forces, it's conserved. A conservation equation is something that's absolute. It's conserved. It doesn't have any caveats. Mass. Mass is conserved. So I could have mass conservation. Another one? Energy conservation. Now, of course, always, mass is not conserved in a relativistic problem. Okay, we're avoiding relativity here. In this class, we will not do any problems of relativity. Okay, finally, a constitutive equation is problem specific, and it has parameters. So for example, Newton's constitutive equation of viscosity. It has a parameter, mu. Not every fluid is a Newtonian fluid. Even amongst Newtonian fluids, some of them have a high viscosity, some of them have a low viscosity. Fourier's law of heat conduction. That doesn't always hold. But you have a thermal conductivity or thermal diffusivity in Fourier's. Fick's equation of diffusion. That's even worse. That holds in class. It doesn't hold that often. A lot of times it doesn't hold in the real world. But it's pretty decent. It has a diffusivity. So all those are constitutive equations. What else is a constitutive equation? In kinetics, the constitutive equation is the rate of a reaction. It has a parameter, K times the concentration to a power. That's a constitutive equation. For this particular reaction that we are running, experimentally we've determined that this is the constitutive equation. The temperature dependence of a rate constant, that it has an Arrhenius law, that is a constitutive equation. There's an activation energy and how it depends on temperature. Those are all examples of constitutive equations. And when you put together a model, you generally use either explicitly or implicitly all of these when you do a fundamental model. Okay, so what is the algorithm or the flow chart for modeling? How do we do modeling? So this is going to be super general, so it's not going to have a lot of content to it. So the first thing we do is we have a sense of goals. So as control engineers, we know what our goals are. We've spent a fair amount of time talking about them. The second thing is we have to formulate a model. And what's involved in that? The first thing is identifying the variables. All the variables that are important, all the things that can change. Then it's making assumptions, simplifying assumptions. never try to solve the most general model. It's too hard. So simplifying assumptions, for example, is choosing. Are we doing lumped or distributed parameter? That's an assumption. If it's lump parameter, we're assuming that's going to give us enough information. The choice of model depends on what our goals are. How specific do we need an answer? Do we need an answer on the molecular level, or do we need it on a reactor level? Or do we need it on a sub-reactor level? It all depends what our goals are. So the simplifying assumptions are important, and then we come up with equations, and we formulate equations. So all that comes in terms of in formulating a model. Then we try to solve the model. And as we saw, there are many ways: analytic, numerical, analog. I have to choose a way, choose a method. For solving. And then I have to carry out that method. But we're not finished when we have a solution to the model. Then we have to validate the model. And you validate by comparison with experiment. And if the model does a good job on experiment, great. But if not, you have to go back and reformulate the model. That is, you have to re-examine your assumptions, re-examine your formulation. Now, let me just divert into philosophy for a second. A model, say, if it has a mathematical model, in principle applies to an infinite number of situations. An infinite number of situations. Parameters can vary continuously in my model. I can only validate a finite number of experiments. That's a problem. Finite versus infinite. So, a famous philosopher of science, Karl Popper, if anyone likes to read philosophy, thought about this, and he said, in science, we have two kinds of models. Ones that are already been proven wrong, and the ones that are still hanging. And that's a pretty pessimistic approach. But you've only got two possibilities. The ones that we know are wrong, and the ones that might be wrong. You never can be sure that a model is right. But what happens, and that's because you can only do a finite number of experiments. There's always the possibility that if you did just one more experiment, you'd find out this model is crap. Like, that's a technical term. So people thought, since Isaac Newton, for 200 years, they thought Newton's laws are correct. And then at the end of the 19th century, they started being able to do experiments where they could access velocities, they could do accurate measurements of things that are happening close to the speed of light. And they found things that were wrong. Newtonian relativity didn't work. When they started to do experiments on the diffraction experiments, shining light through a slit, instead of getting something continuous, they got lines. Didn't make any sense in Newtonian mechanics. So, and that led to quantum mechanics. So even Isaac Newton, probably the greatest, Einstein and Newton, the greatest physicists ever, even Newton's theories that people thought were correct eventually fell apart. Now, that doesn't mean you throw the theory in the garbage. It means you realize where it applies and where it doesn't apply. So that's a little bit of philosophy. You didn't realize that was part of this course, a little bit of philosophy. Okay, so why don't we go through, are there any questions on this before we look at an example? Just see how we're doing on time. Okay, just a little while. Okay, so again, our choice of types of models has to do with the simplifying assumptions have to do with our goals. How accurate do the models need to be? The more detailed our goals are, if they require more detailed information, I need more detailed models. If I don't need as detailed information, I don't need as detailed models. Okay, so why don't we start with a particular example? So let's look at the following example. So I have a tank with a mixer. And there's an outlet. It comes out here, it goes in there. And I'm going to assume that the inlet, CA in versus time. Notice in a lot of books, they'll write a CA0. I hate CA0 because it doesn't tell me anything. I usually use CA in, so you know it's the input. Unless I identify a 0 on the graph, I don't use it. I use it CA in. None of the books do, but this way you know what's going on. So let's assume that for t less than 0, CA in was one value, and then at t equals to 0, I have a step change in CA in. And the question is, what happens to CA out? Well, what happens to CA out? So there are a lot of things I need to figure out here. So that's my question. My goal is to figure out what CA out is. Well, now I need to formulate a model. Well, I need some assumption. I need variables. Obviously, what are my variables? Well, I've got a volumetric flow rate, VA in, and I've got a volumetric, and I've got CA out, V out, where V is the volumetric flow rate, the way kinetics people write it, reaction journal people write it. There's a small v. So obviously my variables, well, the ones I can control, the ones I can manipulate, I can manipulate V in, there's no A, I'm sorry, V in, and CA in. And the ones I can't manipulate, the ones I can't manipulate, can't directly manipulate, or the ones I'll observe, are V out and CA out. Now notice, here I've assumed there's no reaction. In this problem, no reaction. We're given there is no reaction. So we want to know what's happening. All right, so I need some assumptions, or I want to be given something. So we can call this either given or assumptions. So the first thing is I would like to assume, or I'd like to be given, that before t is equal to 0, for t less than 0, the system was in steady state. I'd really like to assume that, or I'd like to be given that. So that means that for t less than 0, I was at some sort of steady value. Now, I'd also like to assume, I don't have to, I can assume that the volume doesn't change with time. It might not. So I'm going to assume, but I don't have to, that the volume is fixed. That is, the volume of fluid doesn't change with time. And then I'm also going to assume that it's a CSTR. Have you heard about CSTRs? I'm using this term as if it were English. The CSTR stands for continuously stirred tank reactor. Or somebody can put an F in here, and they call it continuous flow stirred tank reactor. And the idea of a CSTR, for chemical engineers, it's as English word as vanilla. A CSTR assumes, what are the sub-assumptions of the CSTR? It assumes that the concentration in the reactor doesn't depend on position. The concentrations in the reactor and in the effluent, the outstream, are everywhere the same. The technical word is uniform. It's the concentration uniform. Everywhere here and in the outstream, the concentration is the same. So that's sure. The second assumption says, assume, you don't have to, that the volume is fixed. In other words, I'm assuming that it didn't start out empty. It was already at a level, and then it doesn't go over and it doesn't go down. Sure. But believe me, I'm happy to read anything I write because my handwriting is awful.
Just clarify whether or not the variable V in the other terms of the volumetric flow rate.
Yes, for little v, I'm talking volumetric flow rate, which is in units of length cubed per unit time. The concentration is in units of moles per unit length cubed. So those are the units. It's always important to know the units. Volume, obviously, is in units of length cubed. Other questions? Okay. Yeah. So now, of course, there's a bunch of things that you know you have parameters. So another thing I'm going to assume here, which I don't have to make the problem simple, is I'm going to assume that the density doesn't change. That when I change Ca, the density is not changing. So I assume that the density is uniform and constant. Uniform means it doesn't change in space. Constant means it doesn't change in time. It's the same everywhere. And of course, if I were worried about temperature issues as well, then part of the things I would need to know is I would need to know the heat capacity, for example, if I were interested in the temperature. But I'm not really in this problem. So there are all sorts of things that I might need to know. If I had a reaction going on that involved a phase change, I would need the phase diagram as given information. These would be given information. Any questions on that? Okay, so now let's talk about the formulation. The formulation of the problem depends on what we're looking for, on what, in any given problem, the equations we need depend on the questions. So for example, if we had a problem we were only interested in the total mass, we were only interested in how much mass is in my system, then all I would really need is a conservation of mass equation. I'd look at mass in, mass out, and take the difference, and that's the mass accumulated, because I can't create or destroy mass. If I'm interested in this problem, in the amount of the concentration A in the outlet, then the total mass isn't enough information. I need to do a species balance on A. So because I'm interested in Ca out, I need a species balance. I didn't write it down. I need a species balance. If I were interested in the temperature, if there was some sort of heater involved, or there were a loss of heat through the walls, and I would need also an energy balance. But if I assume that the system temperature doesn't change, I don't need an energy balance. So for example, if this were a gas and not a liquid, and I was still just interested in Ca out, well, if the temperature would change, then even though I would be interested in the concentration, the gas expands and contracts at different temperatures. So I would be forced to have the energy balance as well. But if I'm assuming I'm dealing with a liquid, then I don't need to do that because the coefficient of thermal expansion of a liquid is very small. Questions? Okay, so constituent equations. If I were dealing with an energy balance, I would need a thermal conductivity for Fourier's law. If I were dealing with chemical reactions, I would need rate equations for each reaction. I don't need that in this problem, etc., etc. What else can we say? Now, how many equations? In a given problem, I need to know, when do I have enough equations? When do I have enough equations? Well, what I do is I look at the number of unknown variables. So here are 2 variables that are unknown. And I need to look at how many equations I have. If I have 2 variables and I can come up with 2 equations in terms of those variables, I'm done. If I have more variables than equations, then the system is underdetermined. If I have more equations than variables, the system is overdetermined. I can't satisfy with 2 unknowns 3 equations. Unless I'm very lucky and one of those equations is a linear combination of the other 2. Then I really have only 2 equations. Now, let's notice that over here I have 2 unknowns. And when it comes to constitutive equations, I need a constitutive equation for V out, the volumetric. So here is one of them. Here is the constitutive equation. Let me give you another possibility. Possible, this is board number 3. Constitutive equations for V out. So A, the first one is, of course, the density is constant and uniform. That's equivalent to saying that V out is just equal to V in. If the density doesn't change and there's no reaction, well, then the flow rate in is the flow rate out. Obviously, if I have a gas and the temperature changes, it's going to expand or contract, so that's not going to be true. Similarly, if I have a chemical reaction in a gas that changes the number of moles, A goes to 2B. Now, it's going to expand, so V out is going to be different from V in. How about another one? Let's say I have a liquid and it looks something like this level problem. I'm not pumping it out, I have a hole in the tank. So here's a tank, and I have an outlet here, and there's a fluid here, and there's a height outlet difference. So this is Z is equal to 0, and this is Z is equal to N. Let's do a Bernoulli's equation on this problem. Let's compare point 1 and point 2 using Bernoulli. Well, if you remember, Bernoulli says P0 plus 1/2 rho U squared plus rho GH is the same at both points. At point 1 is equal to the same thing at point 2. So it's a simple Bernoulli's equation. Now, what I would like to do is compare this for different heights. Eventually. But right now, let's look at point 1. At point 1, at 1, P is P0, yes. Well, P0 is always in there. I can assume if this is much bigger than this, a cross-section, that this velocity is very tiny. This velocity is tiny compared with that. So this is pretty much close to 0. And rho GH just becomes rho GL. And P0 is P0. That's at point 1. Let's look at point 2. At point 2, this is still exposed to the atmosphere, so I still have P0. But the velocity is very much not equal to 0. But the height is 0. Because C is 0. Rho G 0. So let's set them equal to each other. If I set them equal to each other, P0 cancels, and I have this is equal to that. And I have 1/2 rho U2 squared is equal to rho GL. And when I say L, really what I should say, well, L is good enough. I can say that this is L1 and this is L2. So this is L2 minus L1. Just to make it look a little more general. Yes? I'm sorry? So this is PA, the atmospheric pressure. PA is the atmospheric. The pressure in here can change, but this is exposed to the atmosphere, this is exposed to the atmosphere. So we're not saying that the pressure here is PA, we're saying the pressure outside, at point 2 is outside of the tank. So outside of the tank, the pressure is PA. Inside the tank, the pressure is higher than PA, otherwise I have nothing pushing the fluid out. So you're absolutely right. Yes, ma'am. Any other questions? So notice, if I solve for U2, U2 is equal to, rows cancel, is equal to G L2 minus L1 times 2 times the square root. And if I want to look at the volumetric flow rate out, that's just equal to the cross-sectional area A2 times U2. Where A2 is the cross-sectional area of the opening here. So what have we determined? What we've determined is, here's another constitutive equation for V out. Right? This constitutive equation for V out says V out is proportional to L2 minus L1. And the constant of proportionality should be something like the cross-sectional area of this opening times the square root of 2g. But typically, if you actually measure it, you don't get exactly that value, so you make that constant empirical. And that's something that's going to come up throughout the semester. Okay, I should probably wind up now, because the hour is just about over. So let's see where we are before we go on, before we break for the day. So we spoke about strategies and issues that come up in control that are more subtle than just yes control, no control. We spoke about these issues, and that gave us a set of questions which we saw we had to answer with models, of which there were many choices. We like fundamental models when possible. We discussed what goes into a fundamental model. And we spoke about how we actually do modeling. Goals, we know how to do that. Formulate a model. We just went into the formulation of the model in great detail. Identify variables, simplifying assumptions, formulate equations. Notice here, V out and CA out are the things we don't know. We don't control them directly. So we need equations for them. The equation for CA out is the species balance. The equation for V out is a constitutive equation. The constitutive equation is either this one, or some other one. And that's where we're up to. We've identified the variables, we've done simplifying assumptions. We haven't written out the equations. We identified which ones we need. We need a constitutive equation. We have two choices. There could be others. We know we need a species balance for CA out. That way we will have two variables, two equations. If we don't make this assumption, then the level in the reactor will also be a third variable. Will be a third variable, V. If we don't make that assumption, and then we will need another equation, and that will be a mass balance to tell us the volume of the reactor. But we made the assumption that we're not doing it. But if we did need it, we would have three variables. We would need a third equation, which is a mass balance. We will pick up next time by writing down the equations, solving them, and doing the validation. And I will derive for you the equation for the CSTR as well as for a plug flow reactor that is unsteady. Unsteady and non-constant density. In your kinetics class, you generally will probably only see the steady state version and not the general non-constant density version. So I will give you the much more general. And I'll talk about some really cool applications that apply to evolution. So viral evolution that actually would apply to, say, possibly to the coronavirus. Are there any questions? Thank you. So if anyone could please help Renee how to make the YouTube channel, that would be wonderful. And the person who took the pictures last time had a great camera. It was super clear. So if you could please take pictures again, I will post them.